Hey guys, how's everyone doing today? Doing good myself. Good to hear. Good to hear. Alrighty. So today we're going to finish up talking about vector line integrals, or integrating vector fields over curves. And then we're going to start looking at next chapter, conservative vector fields. So line integrals of vector fields, continued. Okay. Right. All right. So we looked at how to integrate a scalar function over a curve, do a line integral of a scalar function, and also how to do a line integral of a vector field. And basically, both of those boil down to you parameterize your curve if you need to. Being mindful of the orientation for the vector fields, at least, we'll see later that it doesn't matter for integrating scalar functions. So you parameterize, you replace x, y, and z in the function you're integrating, whether it's a scalar function or a vector field. And then dr becomes r prime t dt, and ds, if you're integrating a scalar function, becomes magnitude r prime t dt. Okay. So we saw, so far we've been integrating over what we would say are smooth curves. All right, so we say a curve is smooth. This is not a technical definition here, but we say a curve C is smooth in this class, basically, if you can parameterize it in one go, right? If you can do a single parameterization to express the entire curve. So if you can parameterize it with a single, I won't explain what this means, but a single smooth vector function R of t. Right, so if you have a circle, a unit circle, right, going around counterclockwise, you can let x be cos t, y be sine t. So then R of t, x t cos t, or sorry, sine t cos t. Sorry, cos t sine t. T goes from 0 to 2 pi, gives you the entire circle. That's not always going to be the case, though. We can integrate over curves where we have to break it up into pieces. So we say C is piecewise smooth. If you can break it up into finitely many smooth pieces. So if it consists of finitely many pieces, C1 up to Cn. Right, so something like this, right? If you've got your kinks in there or something like that, you're not going to be able to parameterize the whole thing in one go. You're going to have to parameterize it piece by piece. But as long as there are only finitely many of them, and each one of those are smooth, so say C1, C2, C3, C4, C5. We say this whole thing is C. Let's say we're going this way along here because we need to be mindful of orientation. The whole thing is C, but it consists of finitely many connected smooth pieces. We say it's piecewise smooth. So far we've only integrated over smooth curves, but we can also integrate over piecewise smooth curves as well. So I'm going to say, we say, in this case, C is equal to, I think the book just uses plus, which is reasonable. So I C is equal to the sum of these guys. C1, it's really the union of these, but that's fine. C1 plus C2 up to Cn. That's how we write C. Each of those guys are the piece, the smooth subcurves. Okay. So if C is piecewise smooth, then how do we integrate over C? Well, that's pretty easy. If we integrate a vector field over C, oops. We just integrate over the first curve, the second curve, etc., and add them all up. These are supposed to be dots, by the way. So each of these pieces are smooth and can be parameterized by a single function, right? Well, they can each be parameterized by different functions. So we look at the first piece, we parameterize if we need to, and then follow the thing and do that integral, and then go on to the second piece, parameterize it differently because it's a different piece, and then do that integral, go to the third piece, etc. And then we do all those integrals and we add them up. So the point is, you can't parameterize a piecewise smooth curve. With a single function, you have to break it into pieces, each of which can be parameterized by a single function. And then we integrate over each of those pieces and then add them up. Okay. So let's do an example. All right. So let's evaluate the integral over the curve C of the vector field F, where here F is going to be e to the z, e to the y, x plus 1. It's our vector field. And C is going to be the triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. And because we're integrating a vector field, we need to specify an orientation on this triangle. So it's going to have the counterclockwise orientation when viewed from above. So if you're like up in the z direction looking down on this, you're going around it counterclockwise. So let's do a quick sketch. Okay, so our vertices are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that's our triangle. So if I start at 1, 0, 0, if I start at 1, 0, 0, and I'm going around counterclockwise when I'm looking at it from above, is the next vertex I'm going to 0, 1, 0 or 0, 0, 1? Which direction am I going? So from 1, 0, 0, am I going to 0, 1, 0 or 0, 0, 1? So we're going to 0, 1, 0, right? So we're looking down on it, and we're going around counterclockwise. That means we're going in this direction. Whoops. My goodness. So that's the orientation of our curve C. Okay, so this is piecewise smooth because and not smooth because it consists of 3 line segments. Each of those line segments we can parameterize, but we can't parameterize the whole thing with a single smooth vector function. So what we're going to say is we're going to say this guy down here from 1, 0, 0 to 0, 1, 0 is C1. This guy is C2. And this guy's C3. And we're going to do each of these integrals separately. I'm not going to do all 3 of them. I'm going to parameterize all 3, and then we're going to do one of the integrals, and then we'll just, the other 2 work the same way, and we'll sort of fill in the blanks there. But let's parameterize these guys. Okay, so like one of the few things we're going to actually ask you to parameterize in R3, to parameterize yourself, are going to be line segments. So remember, so the line segment, so if we start at a point A, so it's a point A, but we'll look at the position vector for that point. and we'll call that the vector A. So the line segment from A to B is going to be, the way we parameterize that, recall, is the position vector for the first point plus t times the difference, b minus a. And t is just going to go from 0 to 1. So that's our parameterization. So where you're starting plus t times where you end minus where you start. And t just goes from 0 to 1. Very easy way to parameterize line segments. Let me just erase that there. That's fine. Okay. So with that in mind, C1, we start at 1, 0, 0. We end at 0, 1, 0. So we'll say this guy, we'll call it R1 of t. So start at 1, 0, 0. So plus t times, we end at 0, 1, 0. So 0, 1, 0 minus 1, 0, 0. And let me give myself some space here. We'll do those on the next page. And let's bring this all together to write it as a single vector. So we have in the first component 1 plus t times 0 minus 1. So 1 minus t in the first component. Second component is 0 plus t minus 0. So t. And third component is 0 plus 0. And t goes from 0 to 1. So another way to think of this is look at each component. So in the first component, look at where you start, and then plus t times the change from where you start to where you end in each component. So for the first component, if we just wanted to do it like that, we start at 1, because we're at 1, 0, 0. If we're just looking at the x coordinate. So we start at 1. We end at 0 for the x coordinate. So we go down by 1. So it's 1 minus 1 times t. So 1 minus t. Second coordinate, y, we start at y equals 0. We end at y equals 1. So 0 plus 1 times t, which is just t. And the third component, z, start at 0, end at 0. So that's just 0 plus 0 times t, which is 0. So that's our R1 of t. Oh. Why does it do this, dude? Oh my goodness. Okay, there we go. All right. And then I'll just go ahead and write down the other two, doing the same thing. So C2, we'll parameterize that by R2 of t. So x, we start at 0. We end at 0. So that's going to be 0. Y, we start at 1. We end at 0. So that's minus 1 times t. And z, we start at 0. We end at 1. So that's 0 plus 1 times t, which is just t. And then for C3, we'll parameterize that by R3 of t. X, we start at 0, end at 1. So that's minus t. Nope, sorry. 0 plus t. Y, we start at 0, end at 0, so that's 0. Z, we start at 1, and we end at 0, so that's 1 minus t. Okay, so these are the parameterizations for the three pieces of the triangle. And we're going to integrate the same vector function, or the same vector field, over these three different curves, using these three different parameterizations. Okay. All right, so we'll integrate over C1. And then I'll tell you what the intervals are for C2 and C3. Okay, so C1. So just a reminder, okay, R1 of t, we said was 1 minus t, t0. T goes from 0 to 1. So we want the integral of the vector field. You know what, let me just write in that vector field. So I don't have to go back. So that was e to the z, e to the y. Sorry, x plus y. So we have our parameterization now. We need to go to the vector field, replace x, y, and z with the parameterizations. And then dr becomes r prime t dt. So what's our r prime t going to be? So r1 prime t. It's going to be negative 1, 1, 0. Right. So we integrate from 0 to 1. E to the z, e to the y, x plus y becomes e to the 0, which is just 1, e to the y, which is t. So e to the t. And then x plus y is going to be 1 minus t plus t, which is 1. And then we said our r prime of t was negative 1, 1, 0. So taking this dot product, so e to the 0, 1 times negative 1, so that's negative 1. E to the t times 1 is just e to the t. So that's our integral. And when we evaluate that, we just get negative 2 plus e. Okay, so that's the integral over the first piece, C1. Then we do the same for C2. I'll write that bit down. So we said R2 of t is going to be 0, 1 minus tt. T goes from 0 to 1. And then because we're going to need it, R2 prime of t is going to be 0, negative 1, 1. You know what? I'll just set up this integral. That's fine. So the integral over C2, we're still using the same vector function, e to the z, e to the y, x plus y. So going there, replacing x, y, and z with the parameterizations. Remember, now we're using the new parameterizations for R2. So e to the z is now e to the t. E to the y is now e to the 1 minus t. And then x plus y is going to be t plus 0. So we dot that with 0, -1, oops, 1. And we get the integral from 0 to 1 of t minus e to the 1 minus t And when we do that, we get 3/2 minus e. And then, rather than going through the whole process again, which you would normally have to do if you're evaluating, I'll just tell you. When we do the same for the integral over C3, we get e minus 3/2. Shouldn't it be 1 minus t? Oh, sorry, yes. 1 minus c for x plus y. Yep, you're right. Yes. My bad. I was looking at x plus c.
Professor, before you go to the next page, I kind of got behind when you have the integration from 0 to 1 for C1. Is that e to the u, or what is that e to?
What, which one?
For C1, it's the integrate. It's like your last line of, or your second to last line. It's 0. Okay.
Yes. Sorry. No use in here. Yeah.
Oh, you're good. That's why I was so confused.
Yes. Okay. That makes more sense. Okay. You think you missed when the order changes for r prime of t? What do you mean?
When it went from -1, 1, 0 to 0, -1, 1. I don't know if it was supposed to be like that. I missed what happened.
So it depends. So just like forget about everything that happened before. When we're integrating over like C1, or we're only looking at this is our vector function that we're parameterizing with. So that's R1. When we integrate over there, we need R1 prime of t. And so when we take the derivative of 1 minus t, t0, we get -1, 1, 0. So when we do C2, we use a different parameterization. We forget about what happened in C1. And this is what we're using now, R2. 0, 1 minus tt. And then when we take the derivative of R2 prime, we get 0, -1, 1. Does that answer your question?
Yeah, thank you.
Okay, so we have the integral over each piece. And so the integral over C is just going to be the sum of those. So it's going to be the integral over C1 plus the integral over C2 plus the integral over C3. I'll just write it in, that's fine. Which we said were, so over C1 we got, what was it? -2 plus E. C2 we got 3/2 minus E. And C3 we got E minus 3/2. And so we just get -2 plus E. Because the 3/2 minus E and the E minus 3/2 cancel. Okay, so yeah, the piecewise smooth curves, we treat the same, except now you have to treat it as several different curves. And each one of those you parameterize separately. Forget about what happens in the other ones. And then you calculate the integral over that piece. Right, so your R prime is going to correspond to the R for that piece. And then you add them all up, and then that's the integral. So one really important thing I want to mention is how orientation, or how changing orientation affects the integral when you're doing line integrals of vector fields and line integrals of scalar functions. So just as a bit of notation, if C is an oriented curve, we say negative C is going to be the same curve, but the opposite orientation, right? So you're moving along the curve, the same curve, but in the opposite direction. So remember, if you have a given curve, there are two different orientations, right? If you look at 2 points, the two endpoints on the curve, or if it's a closed curve, just it starts and ends at the same point. One orientation goes from starting P to Q, the other goes from Q to P. Or if you're a closed curve, one goes around one direction, the other goes around the other direction. But those are the two different orientations for a given curve. Okay. So for scalar line integrals, we didn't mention orientation because it turns out it doesn't matter. So for scalar line integrals, if you change the orientation, so if you integrate a scalar function over the opposite orientation, that's the same as, we get the same integral. Right, so if you change the orientation of your curve, and you integrate a scalar function, you get the same answer. Changing the orientation doesn't affect the integral for scalar integrals. So just a regular function of 2 or 3 variables, if you're integrating that over a curve, orientation doesn't matter. But if you're integrating a vector field, changing the orientation flips the sign of the integral. So if you change the orientation, you get negative of the integral. And this is important. Definitely remember this. So for scalar functions, the integral doesn't change when you flip the orientation. You get the same answer. For vector fields, you change sign. You get negative. Of the integral when you flip the orientation of your curve. And why is that? Well, remember, Another way we can write these is f dot t ds. And remember, t is the unit tangent vector. What happens to the unit tangent vector when you change orientation? So the unit tangent vector is tangent to the curve. So if you pick a point, you have the same tangent line, but the tangent vector points in the direction of travel. So if you change orientation, you get a parallel vector, but pointing in the opposite direction. And since it's unit, it's just -1 times that. So if you change the orientation of your curve, t becomes -t. Sorry, this is very difficult to write this small with my finger. Sorry. Oh my God, why are you doing this to me? There we go. So instead of f dot t, it just becomes f dot -t, which is negative of the original thing. And that's why it switches sign. So scalar functions don't change. Vector fields change sign. Remember that. Okay, and one last thing I want to mention for applications. We won't do any more examples, but just sort of a different a way a question could be worded is if you have a vector field F, so we say the work done by a vector field F on an object moving along, object or a particle or whatever, moving along an oriented curve C. So we say the work done by a vector field as you move along a curve C. If you have a question that says, what is the work done with this vector field as you move along a curve? That's just the integral of the vector field along the curve. Whoops, sorry, the work done by F. So the work done by a vector field as you move along a curve C is the integral over the curve C of the vector field. So you could also say the work done against a vector field. Whoops, against vector field F. So the work you need to do against F to move an object along a curve C. My goodness, I cannot spell today. That's going to be negative of the integral over the curve C of F dot dr. So the work done by a vector field is the integral of the vector field. The work done against F, a vector field F, is negative of the integral. Okay, and that's all I want to say about that. It's just a bit of a nomenclature. Okay, so we have a few minutes left. I want to just briefly start talking about conservative vector fields and get to kind of the big theorem about conservative vector fields. Why conservative vector fields are so nice to integrate over. So recall, we say a vector field F is conservative if there's a scalar function, little f, we call it the potential function, or sorry, a potential function. If this is the case, such that our vector field is the gradient of that potential function. So a vector field is conservative if there's some scalar function where when you take the gradient, you get this vector field. So think of taking the gradient as taking a derivative of this function in a way. So we think of the potential function, little f, as an antiderivative. And it's gonna, we'll see later that it's gonna work like an antiderivative. Of our vector field. So our potential function is basically going to be like an antiderivative. So you're conservative if it has an antiderivative, right? So if there's some scalar function where when you take the gradient of it, you get the vector function. Okay, so we haven't seen, we have, but we haven't said exactly how. We haven't quite seen, and we'll see this next time, how to check that a vector field is conservative. Well, we have seen it, but we'll say that's exactly how we do it. And we also haven't seen, once we know a vector field is conservative, how to find a potential function. We'll look at that next time. But let's just assume something's conservative and then see what we can do with that. So that's a conservative vector field. They're very, very nice, as we'll see in a second. Okay. So just a bit of notation. Oops. So if C is a closed curve, a closed oriented curve, so in other words, it starts and ends at the same point. So if it's a closed curve, we say the integral over a closed curve C is called the circulation. So it's the circulation of F around the closed curve C. So C is closed, and we integrate a vector field over that closed curve. We say that's a circulation of the vector field over that curve C. And if it's a closed curve, just to emphasize that, instead of just writing the normal integral sign, we'll write an integral sign with a little circle on it. So if you see that integral sign with a little circle, all that means is a line integral over a closed curve. It just means C is a closed curve in that case. Okay. So one more bit. Really quickly. Oops. So we say a vector field is path independent So we say a vector field is path independent if the integral only depends on the endpoints. So it only depends on the endpoints of the curve. Whoops. And not on the path between the two. So what do I mean by that? If you have any 2 points, say P and Q, we say for any 2 points, so F is independent if for any 2 points you pick, if you look at one path from P to Q and another path from P to Q, say C2, then the integral over C1 is going to be the same as the integral over C2, because all that matters are the endpoints, the starting point and the ending point. It doesn't matter how you get from point A to point B, you're going to get the same integral no matter what path you take. And that's true for any 2 points. That's what path independent means. Okay, so here's the big theorem, and we'll end with this. This is why line integrals of conservative vector fields are so nice, because essentially you don't really have to do a line integral, as we'll see. So suppose our vector field F is conservative. In particular, it's the gradient of little f. So F is conservative, and the potential function is little f. If C is any curve from a point P to a point Q, then the integral over the curve C of the vector field F, it's going to work just like in 140. You just evaluate the antiderivative at the endpoints. So it's the antiderivative, little f, at the final point minus the antiderivative at the starting point. So this means f is path independent, the vector field. Oops. So that's really nice, right? You don't have to parameterize, you don't have to do a line integral. You just have to know what the antiderivative is, the potential function, and you have to know the starting and ending point. And if you know those things, then it's really easy to evaluate. You can skip the whole process of doing a line integral if your vector field's conservative. So part 2, if you're a closed curve, you can think of that as starting and ending at the same point. And so applying this, applying number 1, if you're starting and ending at the same point, then you're evaluating the antiderivative at the same point. And so you end up with 0. So if C is a closed curve, then the integral of a conservative vector field around that closed curve is always 0. So if f is conservative, the integral around any closed curve is 0. Because you can think of it as starting and ending at the same place. P and Q are the same. So you get f of P minus f of P, which is 0. Okay, so that's why conservative vector fields are so nice. Next time we'll see how to check that a vector field is conservative, and if it's conservative, how to find the potential function or a potential function. And then if we can do those, which are pretty easy, then we can easily evaluate these line integrals without doing a line integral, which we would like to avoid if possible. We could just use the theorem. Okay, that's it for today. If you don't have any questions, then have a great weekend, and I will see you guys on Monday.